Good morning, all students.
Good morning, sir.
Physics lecture is completed.
Yes.
So, last lecture we already started this nucleophilic substitution reactions of alkyl halides. Remember, and for the board examination, this table is very, very important. I already told you, one reaction 100% it will be asked from this table. So we discussed this, how the alcohols can be prepared by using alkyl halides. There are two methods by using aqueous KOH or NaOH, that is aqueous alkali, when this methyl chloride is treated with aqueous alkalis. So we are using the two types of alkalis here, NaOH or KOH, undergoes hydrolysis, and this iodine is replaced. So in all these reactions, we have to remember, this is very easy to understand. Nucleophile is substituted here and the halogen it will be removed. Okay, so we have to remember this method for all the nucleophilic substitution reaction. Nucleophile, you should know which is nucleophile and how the nucleophile is generated, and that nucleophile only we have to place in place of halogen. Okay, mute yourself, don't disturb others. So there are two methods of preparation of alcohols by using alkyl halides. Remember, if the aqueous KOH or NaOH is not available, the second method is moist Ag2O. Ag2O, that is the silver oxide. When it is in moist condition, when water is added, it gives AgOH. So AgOH actually doesn't exist. It is prepared in situ. Like NaOH or KOH, you cannot add KOH, means it is not prepared in bottles and we can add in the reaction mixture. This is not possible. At that time, at that instant, it is called as in situ, it is prepared when silver oxide, moist silver oxide means some water molecules are there. It is called as moist silver oxide. It generates AgOH and this AgOH reacts. So this reaction and these two reactions already we completed. Now I'm discussing this formation of alkyl cyanides. So these reactions we have to make a practice at your home. You can take any alkyl halide here. Instead of CH3I, we can take CH3Br, you can take CH3Cl, or you can also change this R group. Instead of methyl, you can take the ethyl group also, or any R group, isopropyl group, or any whatever you like, you can take any R group here. So general reaction is very important when the alkyl halide is treated with KCN. KCN is here potassium cyanide, and alcohol it is used as a solvent. Boil, reflux. So this, which is a nucleophile here, cyanide. This Cn minus, it is a nucleophile. It will be replaced. Iodine will be removed here, and this iodine will combine with this potassium and we get the Ki. So here we have to remember one important thing. When the KCN it is used, that is potassium cyanide it is used, this is actually the ambient nucleophile, KCN and AgCN. These are the ambient. In the next slide I will explain what is this ambient nucleophiles. First, I will explain this reaction, formation of isocyanides or nitriles when the same alkyl halide or CH3Ci, or we can take here any ethyl chloride or ethyl bromide, any alkyl halide, if you take here any alkyl halide and AgCN if it is added. Now, in the previous reaction, we are adding the KgCN. In this reaction, we are adding the AgCN. So what is the difference here? Alcohol, it is used as a solvent here. Mute yourself. So what is the change? I will explain. In the previous reaction here, alcohol, it is used as a solvent, but in this reaction, you are not using alcohol, only heating is sufficient. So if the AgCN, silver cyanide, it is added. So again here, cyanide is nucleophile. and Cl is a halide halogen here. So it is replaced, but we have to remember one thing here. We cannot get here CH3, CH2, CN. We get here CH3, CH2, NC here. NC. This is isocyanide, means nitrogen attacks here. And in this KCN, carbon attacks. And in this AgCN, nitrogen attacks. Why this is happening? Its explanation is given below. So these cyanides and nitrites. Nitrates means NO2. So cyanides means CN, nitrites. I am not calling nitriles. Nitrites means NO2 group. This NO2. These possess the two nucleophilic centers. And these are called as ambident nucleophiles. Here, in case of cyanide, there are two nucleophilic center. Carbon can attack and nitrogen can be attacked. It is shown here. See, CN. So in case of KCN, why the carbon attacks? It is given because KCN is predominantly ionic and AgCN is covalent. So if this KCN is ionic, what happens? It provides the cyanide ion. CN minus, it produce the cyanide ions, and K plus it will be separated, CN minus will be separated. Both here carbon and here nitrogen are capable to donate its electron pair. That's why these are called as nucleophiles. So here carbon-carbon bond, it becomes very stronger. CC bond is very stronger than the CN bond. So attack occurs through this carbon. In case of AgCN, KCN is used. Attacks takes place with carbon. I am explaining this example. Why the carbon-carbon bond is formed? Because CC bond is more stronger than the CN bond. Try to understand. This is the reason why we get here CN. And in AgCN, why you get the NC? The reason is given here. So the carbon-carbon bond is more stronger. Attacks takes place through this carbon, and we get the major product as an alkyl cyanide. And in case of AgCN, what happens? It is covalent in nature. So nitrogen is free to attack. Here nitrogen is free to attack. So attacks takes place with nitrogen, and we get the product isocyanide. This is the change. Same it is happening in case of nitrite also. There are two nucleophiles. Oxygen acts as a nucleophile. Nitrogen is also acts as a nucleophile. When KNO2, same I am showing in this table. So here see KNO2, when it is used, KNO2 potassium nitrite, it is used, attack takes place with oxygen, and we get this product. Okay, so we get this product RONO, and when we are using this AgNO2, we get the product RNO2. Attacks takes place with nitrogen. So this is the very important thing we have to remember when AgCN is used, when AgNO2 is used. Remember, when AgCN is used, attacks takes place with nitrogen, and when AgNO2 is used, attacks also takes place with nitrogen, because nitrogen is free here. And if the KCN it is used, attacks takes place through carbon, and when KNO2 is used, attacks takes place through oxygen. So this is very, very important things I have explained, and 100% the student get confused whether AgCN is used and KCN is used. Please try to understand. These are very important reaction, and other reactions are very easy because directly here see, in case of ammonia is added. If the ammonia is added, so this chlorine, it will be replaced with NH2, and one hydrogen it will combine with Cl, and we get here HCl. So this is a normal reaction, very simple reaction. This is called as ammonialysis of alkyl halide. Ammonialysis means what? Ammonia group is introduced in this methyl chloride. Ammonia group is introduced. This is called as ammonialysis of alkyl halide. Okay, then the next one is formation of ethers. This is very, very important reaction. Make a star. This is Williamson synthesis in 11th standard also. This is included and I explain. So Williamson synthesis is what? It is the formation of ethers. Ethers means this is a functional group of ether. OR. Sorry, this is R O R, or it may be R O R dash, it may be AR O AR, or it may be R O. So it may be alkyl group or it may be aromatic. So when the oxygen is in between alkyl group or aryl group, it is called as ethers. So how the ethers are prepared? Now by using alkyl halides. So first thing, alkyl halides when boiled with sodium alkoxides. Sodium alkoxide, this is a general term it is used. Alkoxide. Okay, this will be changed when the alkyl group is changed, undergoes substitution reaction to form the corresponding ethers. In this reaction, the halide of the alkyl halide, it is substituted by which group? Alkoxy group. I am coming to this alkoxy group. This is OR group. Alkoxy group means OR group. So this reaction is called as Williamson synthesis of ethers. This is the name of the scientist. Now, this RO group or OR group, it is called as alkoxide group, alkyl group, when it is attached to the oxygen. Any R group, when it is attached to the oxygen, it is called as alkoxy group. Suppose this is CH3R group and this is O. So this is called as methoxide because methyl group is attached here. When the C2H5 group is attached to oxygen, it is called as ethoxide. When the different C3, suppose H7, this is propyl group. C3H7, when it is attached to the oxygen, it is called as propoxy. So it is methoxide, this is ethoxide, and this is propoxide, like this. So how it is prepared? When this sodium metal, it is treated with alcohol. Now, this is also asked for the board examination, remember. What is the reaction of alcohol with sodium metal? I think in the 2018 or 2019, not 2019, 2017 or 18, this question is asked. What is the reaction of sodium metal with this one? What is the reaction of sodium metal with alcohol? So we have to take here two molecules of alcohol. This is general reaction shown, R twice ROH plus twice Na. So H2 gas, it will be evolved only. H2 gas will be evolved and we get here alkoxide. So one example is given here, methyl alcohol. We are taking the two molecules of methyl alcohol plus twice Na. So this sodium metal, it is joined to this oxygen and these two hydrogens will be removed. These two hydrogens will be removed and we get this sodium methoxide. This sodium methoxide we have to use in this reaction. So this is the first step. In Williamson synthesis, this is two-step reaction. In the first step, sodium alkoxides are prepared, and in the second step, these prepared sodium alkoxide reacts with the alkyl halides. So here methyl bromide is taken. This is sodium ethoxide because this ethane group attached to the oxygen, it is ethoxide. C2H5O, this is ethoxide because sodium is there. That's why the name is sodium ethoxide. Okay. Then see this bromine, it is replaced because this is nucleophilic substitution reaction. Which is a nucleophile in this reaction? This is a nucleophile, C2H5O. This C2H5O, it will be attached here and bromine will be removed and it will combine with Na. This is the byproduct. So this is the byproduct. NaBr, it is the byproduct and we get the ether. So remember one thing, for the preparation of ethers, we have to use ethers. This is also the ether. See, sodium ethoxide is also one type of ether because see the functional group here, oxygen is in between here sodium and here any alkyl group. So this is very easy reaction. Make a practice, take different examples. So you understand how these ethers are formed by using Williamson synthesis. ethoxides are used. And how the ethoxides are prepared? Ethoxides are prepared by using alcohols. So remember the first step also. This is as for board examination. Now the next reaction is formation of esters. So first, you should know the functional group of esters. This is a C double bond O group. C double bond O group. This is ester. So this oxygen, it may be attached to the R group, or it may attach to the R dash group. R means same R groups, or this side it may be R group. It may be R dash. So what is the difference in R and R dash? So in the same R groups are there, it is called as R. When one is R and one is R dash, means these groups are different, or it may be AR aromatic. It may be aromatic, or it may be AR dash. So these are the different possibilities of esters. These are the different possibilities of esters. So the mechanism is same. See, this is alkyl halide is taken here, CH3I. Instead of this CH3I, we can take here C2H5. C2H5, suppose bromine I am taking, ethyl bromide. I am showing different example. This is different alkyl halide. Plus, we have to use what? Silver salt of carboxylic acid, remember. Silver salt of carboxylic acid. This is silver salt of carboxylic acid means what? What is the carboxylic acid? This is RCOOH. This is the functional group of carboxylic acid. RCOH. This is general carboxylic acid. So in case of formation of salt, what happens? This one. See, AgO C double bond O CH3. Now I will explain how this salt is prepared. CH3 COOH. This is the acid, acetic acid. CH3 COOH. This is the acetic acid. Plus, suppose silver salt we have to prepare. One is acid and one is base. We have to use. Suppose AgOH. Silver hydroxide. This is how it is prepared. Moist Ag2O. This is prepared by using moist Ag2O. So this is the reaction with acid and base. So what is formed? Salt is prepared. So this hydrogen, this OH, it will be combined. Water molecule will be removed, and we get CH3COOAg. How the salt is prepared? CH3. This is the first step I am explaining how the silver salt is prepared. This is not given. This is assumed. You should know how the salt is prepared. When the acid and base react, salt is formed, salt and water. So CH3CO. This is which salt? CH3COOAg. This is silver, because the group which is attached to the oxygen we have to take first. This is silver, and how many carbons are there? 2 carbons. So the name IUPAC name is this is silver ethanoate. Silver ethanoate, and the common name is given in this reaction here, the silver acetate. Silver acetate. This is the common name, and IUPAC name is what? This is the silver, and 2 carbons are there. Ethanoate. Silver ethanoate. So this is the silver salt of carboxylic acids we have to use in this reaction. So this Ag, this is the nucleophile. OCOCH3, this is the nucleophile, minus Ag plus, it will attack, and this iodine, it will be combined with Ag. This is the byproduct, and this is the main product. This is the main product. Ester, see the group, OCO group. OCO group. This is the ester. And how the name is given to this ester? The group which is attached to the single oxygen, we have to take first. This is the methyl and acetate group. This is the common name. And IUPAC name, what will be the IUPAC name? This will be methyl ethanoate, because there are 2 carbons. When the 3 carbons are there, it will be propanoate. When the 4 carbons are there, it will be butanoate. And as the number of carbon increases, the name will be changed. So this reaction is asked for the examination in the February 2019. So remember, make a practice of these reactions. Williamson synthesis, take the different silver salt. It is not necessary to use this acetate. We can take this Ag. We can take this AgO, AgO, change this group CO, change this group CO, C2H5, change this group C2H5. Anybody can tell me what is the name of this silver salt? I want to know what is the name of this salt. Silver, we have to take this Ag first, silver. And what is this? How many carbons are now there? 3 carbons. This is 1.
3 carbon.
3 carbons. So the name will be propanoate, correct? The name will be propanoate, silver propanoate. Okay. So my request to all, take different alkyl halides, take different this silver salt and make the reactions. Make a practice of these reactions. So reactions will be easy. In each reaction, we have to remember nucleophile should be substituted. So this is the reaction with AgCN, KCN. Make a practice of this KNO2, AgNO2, because KNO2 and AgNO2 reactions are not given here. It is expected. It is given here, nitrites. So KNO2, we have to add KNO2. This is potassium nitrite. This is asked for examination now in the latest examination, board examination. So just tell me, if the KNO2 is used, attacks will be takes place with nitrogen or oxygen. Anyone tell me, sir? Anyone tell me when the KNO2 is used, attacks takes place with nitrogen or oxygen? Yes. It is given here, KCN. When the KCN is used, attacks takes place through this carbon. So same when the KNO2 is used, attacks takes place through oxygen, not nitrogen. When the attacks takes place with nitrogen, when AgNO2 is used. Same for AgCN. When AgCN is used, attacks takes place through nitrogen. So we get the isocyanide here. Where it is given here, isocyanide is the product. And same for AgNO2. When AgNO2 is used, same we get the product, attacks takes place with NO2. So in this table it is given. In this table it is clearly given when what is the product when AgNO2 is used. See the product here, RNO2. Attacks takes place through this nitrogen. When KNO2 is used, attack takes place through oxygen. ONO, it is the product. ONO. Same for AgCN, we get here RNC. When KCN is used, we get here CN. So make a practice of these reactions today. Williamson synthesis, Esters. Writing of the reactions is very important. Next part is nucleophilic substitution bimolecular reactions. So this part is completed. All these are nucleophilic substitution reactions. Now we are coming to this substitution nucleophilic bimolecular. What is, there are 2 types of reaction, unimolecular and bimolecular reactions. So detail what is unimolecular reaction, what is bimolecular reaction, it is included in the chapter chemical kinetics. But before that chapter, I will explain unimolecular means what and bimolecular reaction means what. When the rate of the reaction depends upon the only one substrate, this is called as unimolecular reaction. And when the rate of reaction depends upon the 2 substrates, it is called as bimolecular reactions. So these reactions are very long reactions in the chemistry, very bigger reactions. So 3 marks or 4 marks question it is expected on these reactions. I will explain how the question it is asked for the examination. But before that question, you must know what is a SN2 reaction. So SN2, it is a short form. S stands for substitution and stands for nucleophilic, and this 2 is bimolecular. So this is the short form of this reaction. SN2 means substitution nucleophilic bimolecular, and another reaction is SN1 reaction. See, this is SN1, substitution nucleophilic unimolecular reaction. So first we will discuss this SN2 reaction, the reaction between methyl bromide. So we have to remember one thing: in case of SN2 reaction, the primary alkyl halide is used, and in case of SN1 reaction, tertiary alkyl halides are used here. See this, the alkyl halide is tertiary. What is the name of this alkyl halide? Anyone can tell me? What is the name of common name or IUPAC name? Anyone can tell me? Fast. 40 students are there. Anyone tell me what is the IUPAC name or common name? No one? No one is there. So the common name is tertiary butyl bromide. This is the common name, and the IUPAC name will be, this is the longest chain. This is the longest chain. So we have to give the numbering like this. This is number 1, this is number 2, number 3, and the name will be 2-bromo 2-methyl propane. 2-bromo 2-methyl propane. This is the IUPAC name for tertiary butyl bromide. But first we will discuss this SN1 SN2 reaction, and then I am coming to the SN1. Combine by simultaneously I will explain these two reactions. What is the change? Because the difference is also asked for the examination. What is the difference in SN2 and SN1 reactions? Okay. So the reaction between methyl bromide, okay, all of you know the methyl bromide is written here, and the hydroxide ion. This is a hydroxide ion, OH minus. So this hydroxide ion can be generated by AgOH also. It can be generated with aqueous KOH also. It can be generated by aqueous NaOH also. So forget about the reagent. We are interested in nucleophile. So this is a nucleophile OH minus. It is called as hydroxide ion. And when these reacts together, you know what is the product? This is the nucleophile. It will attack here. The bromine will be removed, and we get here Br minus. And if the KOH is used here, this bromine will combine with K, and we get the product KBr. So this is the general reaction. It is shown. This reaction takes place with second order kinetics. Now I will explain what is second order kinetics means. What means? It is explained here. Because the rate of this reaction depends upon the concentration of two reactants here. Concentration, this square bracket indicates the molar concentration. Rate of the reaction is equal to the K. It is the proportionality constant. This is the molar concentration of CH3Br and molar concentration of OH minus. So this, it is written here. This rate of the reaction depends upon the concentration of methyl bromide and hydroxide ion. Okay, hydroxide ion. यहाँ पे ion word चाहिए, hydroxide ion. Okay, so the reaction is called as substitution nucleophilic bimolecular reaction, SN2. Why it is bimolecular? Because the rate depends upon the two reactants, concentration of the two reactants. And in case of SN1 reaction, I am showing you. See, the rate of the reaction is depend upon the K. See, there is only one reactant. That is the concentration of tertiary butyl bromide. Here, rate is not depend upon the concentration of OH minus. In case of SN1 reaction, I am talking about. So simultaneously, I am explaining both the reactions. In case of SN2 reaction, rate depends upon the two reactants, concentration of the two reactants. This is the concentration of CH3Br and concentration of OH minus. So all of you Understand why it is called as SN2 reaction? Because this is the second order kinetics. Rate depends upon the concentration of the two reactants. Now, here it is given rate of the chemical reaction is influenced by chemical species taking part in the slowest step of its mechanism. So actually this part is included in the chapter number 6. Rate depends upon rate of chemical reaction, means speed of chemical reaction. Always it is depends upon the slow step. If the reaction takes place with first step, second step, third step reaction, if the reaction having the fourth step or more than 2 steps, the slowest step of the reaction rate depends upon the slow step. Okay, in the mechanism you have to see the mechanism of the reaction, and in that mechanism which is the slow step, and on the slow step the rate of the reaction depends. So in the above reaction only 2 reactants are present. Okay, these are the 2 reactants are present, and both are found to be influence the rate of reaction. Okay, because the rate is depend upon the 2 species here, and we are assuming these 2 are included in the slow step. This shows that the 2 changes, namely bond breaking and bond formation taking place, bond forming at the carbon takes place simultaneously. Means which bond is broken and which bond is formed, I will explain here. Just a minute. Just a minute. Electricity problem is there. Yes, am I audible?
Yes. Yes.
So I connected to different connection. Just a minute. So anyone can tell me in this reaction which bond is formed and which bond is broken in this above reaction. So I will explain you. See, in this reaction, which bond is broken? This bond is broken. CH3Br. This bond will be broken, and which new bond is formed? CH3OH bond will be formed. Correct? This CH3OH bond is formed, and CH3Br bond is broken. So this breaking of a bond and formation of bond takes place simultaneously in the same step. So the mechanism is given here. See the mechanism. This is CH3Br. We can see this is carbon. This is the hydrogen behind the plane. This is the hydrogen which is shown with this wedge shape, and this is in the plane. This hydrogen, the above hydrogen is in the plane. This dotted hydrogen, it is behind the plane, and this hydrogen is in front of. This is 3 dimension. Suppose we have to assume this is a 3-dimensional CH3, and this Br is also in the plane. So this simple lines, this hydrogen and this bromine is in the plane. Hydrogen, this hydrogen is behind, this hydrogen is front, means to the observer. And see where from where the nucleophile attacks. This is OH minus is nucleophile. Okay, this is a nucleophile, Nu minus. So when this nucleophile attacks always from the backside of this bromine. Anyone can tell me why the nucleophile is not attacking from this side? If the OH minus attacks from this side, what will happen?
Halogen is already.
Because already halogen is there. This is negatively charged. The nucleophile is also negatively charged, so there will be repulsion. So it is very easy for the nucleophile attack from the backside. It is very easy because this much space is available for the nucleophile to attack from the backside of the nucleophile. It is very easy to attack. And from the front side, it is difficult because already this is having the negative charge. Also, the nucleophile having the negative charge, they will repel each other. So there will be the disturbance. there will be disturbance from attacking to the front side. So that's why it is very easy to attack from the back side. So if this is nucleophile is attacked, this is the RDS. RDS is rate determining step. Just I explain you when the reaction takes place in various steps, first step, second step, third step, which is a rate determining step. Slow step is the rate determining step. So in this particular reaction, this reaction is occurs in only one step, and that will be the rate determining step. So in the rate determining step, it is shown this is a nucleophile OH minus. This bond is partially formed. This bond is partially breaking. CH3Br. So this bond will be partially breaking, and the new bond it is partially formed simultaneously. Okay, this is the hydrogen which is behind the plane. This is the hydrogen in front of, so towards the observer, and this is in the plane. So this is called as transition state. Transition state means this is the higher energy state in this reaction. At this particular transition state, see this is unstable, because see the valency of this carbon is 1, 2, 3, 4, 5. So this is very unstable step. This is called as transition state, which is having the higher energy. So after this transition state, what happens? This bond, it will be formed, and this bond will be permanently, it will be broken. Again, the energy will be comes down. Energy will be comes down. Suppose initially I am showing with the help of this graph. Suppose see this graph from this side. The potential energy will be, potential energy is here, and this side is reaction coordinate. So initially the here reactant is there, reactant transition state I am showing here. This is the transition state. Here in this reaction graph is not given, and this is the product. So initially the rate potential energy of the reaction, it will be 0 here when the reactants are there. Now I am adding OH minus. What will happen? OH minus is added, the potential energy of the reaction will increase. At this transition state, it will be higher. At this transition state, the energy will be higher because there is a formation of transition state is very unstable, because the bond formation takes place, the bond breaking takes place here. And if this bond is formed and this is broken, immediately the energy will be comes down. So you understand this graph, why the energy increases, and when the bond is broken, why the energy comes down? Because when the bond is broken, what will happen? Energy will be comes down. And why the energy is higher at the transition state? Because at this stage, simultaneously formation of bond and formation bond breaking and bond formation takes place. That's why the energy is higher here. And again the energy will be comes down, but it will not comes down to the, suppose this is the energy of the reactant. So the graph will be like this. It will not comes to the reactant side, it will be comes here. The graph will be like this. Suppose this is the reactant, it will become to the transition state, and it will comes here. This is the product. So this is the product here. This is the reactant, and this is the transition state. Okay, so the reaction will be occurs like this. This is the graph of the reaction, and this is mechanism. So you understand the mechanism of the reaction, SN2 reaction mechanism. OH minus, it will be attacks from the backside of the nucleophile. This is the transition state, and this is the product. So in the product, we have to observe, see here the position of this hydrogen.